Hello, this is my third video in the Algebra 2 series. Today we're going to be focusing mainly on rational functions, and we'll also do some exponentials and logs as well. So let's just start graphing rational functions. So let's take a look at something like this. This is just already pretty advanced. And so if you can graph something like this, then you can graph a lot of rational functions. So you can see that we can obviously break quadratic factors. Let's see. So we can break it into different squares. Great. So you'll notice right away that we have zeros at -4, and then we also have a 0 at 3. And then that'll help us. We also have a vertical asymptote at -2 and at 2. So we can draw those. So at 2, -2. And you'll see that we have a horizontal asymptote at 1. All right. Sorry, I am a little bit congested. I apologize. So, because we have a 0 at 3, we know the graph's going to look like this. We use asymptotes to guide us. -4 is over here, so it should end up looking like this. Well, oh, sorry. It should be more like, there we go, like that. Approaching the asymptote. Now I have to figure out what happens over here. On the y-axis, we can just plug in x equals 0 for that. So x equals 0, we have 4 times -3 on the top, and then we have what is it? -4 on the bottom, right? Yeah, so we get like 3 up here, or something like that. I hope I did my math right. If I didn't, actually, hold on. 0, 3, oh, we get -12. -12 over -4, which should give us 3, okay. So we have a point up here. We also just need to plug in points around it. I'm going to plug in 1 and -1, so we can actually see the behavior of the graph. So if we plug in 1, we get 5 times -2 on top, so -10. And if we plug in 1, then we get -3 on the bottom, right? Okay, so there's like 10 over 3. That's greater than 3, so like something like that. Like right there. Now let's plug in +1. Wait. Did I plug in 1? Oh yeah, I plugged in 1, sorry, so it should be over here. Not -1, sorry. Making a lot of mistakes right now. Alright, if we plug in -1, then we get, oh, I can just plug it in here. What am I doing? 1 minus 1 minus 12, and then 1 minus 4. -12 over, okay. Get 4. Okay, so now we have the behavior. This is a 4, by the way, of the graph here, and then we get that. All right, and that's how you graph this rational function. It's really messy, but really the main idea is just to use points and the asymptotes to guide you, and then also not screwing up mental math like I did. I'm just gonna move on. I don't want to spend a lot of time erasing stuff. All right, let's try and graph something like this. So as you may know, so when you have equal numerator powers for a horizontal asymptote, you just divide the coefficients. If you have a power greater than the bottom, horizontal asymptote is just 0. However, when you have the power greater than the top, you don't have a horizontal asymptote at all. What you end up getting is what we call a slant asymptote. So a slant asymptote is essentially an asymptote that's a line. And that is a line with a slope. And to find the slant asymptote, you have to use long division or synthetic division and get it, pretty much. So let's do that. Let's just use synthetic division. So we'll get 1, 2, 1, and then, yeah. Okay. And then this just becomes x plus 3. And we ignore the remainder. We don't care about the remainder. It doesn't affect the slant asymptote at all. Okay. Now let's see what this looks like. I should probably put this on Do Not Disturb in case someone texts me in the middle of this. Okay. So all we have to do is graph the slant asymptote as a line. So it's just going to be like this. Except pretend that goes to the origin. Pretend that actually goes to the origin. And you can tell that we also have a vertical asymptote at 1. Okay. So in other words, all we need now are points that describe what the function does, and then we should be good. So I'm going to see if it actually has any zeros. So actually this factors nicely. You know what? I actually have to redraw this because I did it so poorly. And also, wait, what am I doing? I drew the slant asymptote wrong. I'm sorry. That's why. I apologize. It should be 3. It should be like that. There we go. Guys, I swear I remember how to draw lines. I'm sorry. Okay. Alright, this looks better. So now let's actually, plug in points. There's a 0 and -1, so obviously we know it looks like this somehow. And then we just need to plug in a point greater than 1, so let's plug in 2. So we plug in 2, we get 3 squared over 1, pretty much, so 9. 9 should be like up here, so looks something like that. That's how you graph with the slant asymptote. Okay, now let's do a little bit of review on exponential and logarithmic properties. So actually, first, before we do that, let's actually graph some exponential log functions. Okay. If you guys remember how to the characteristics of a exponential graph, it always says vertical asymptote, or horizontal asymptote. And And in this case, it will occur at 3. And you'll also notice that because there's a negative here, this function will exhibit a reflection across the x-axis. So it's going to look a little bit, it's going to flip pretty much what a normal exponential looks like. Let's just get a point. Let's plug in 0. We'll plug in 0. We get 2. So literally, yeah. Let's get another point. Let's plug in 1. What happens at 1? Well, 1 is just equal to 1. So literally all we have to do now, use the asymptote in the 2 points. Boom. That's it. I said I wasn't going to erase. Sorry. Okay. Let's graph a log now. Now, if you're unfamiliar with logs, logs are essentially the inverse function to exponentials. So if you were to ask a question like, okay, what exponent, okay, 2 raised to what exponent is equal to 4? We can rewrite that. We can say log of some base of the number 4 is equal to that exponent. And that's essentially what we're doing. That's essentially what a log does. It flips the answer and it flips the input, and that's exactly what an inverse function is. So anyway, to graph, it's pretty simple. You'll notice that we should have a shift to the left by 5. And that's actually where we have a vertical asymptote, because we can't have negatives inside logs. Now we just plug in a point. I like to plug in a point that makes it 0. Find the 0 of the thing. If you plug in -4, that'll give you the 0 of the logarithmic function. And you can also plug in 5, because log of 10 is just 1. So that gives you 2. Therefore, all you gotta do, even though it should look more like that, actually that's better. There, you know what? You guys get the point. It's fine. Okay. Now on to properties of logarithms. So just like exponents had properties like this, logarithms also have similar properties because they're inverse functions. For example, or another pretty important property is this property. If you have something in here raised to a power, then you just bring that power out. So this is pretty useful. We can use it to condense logarithms or use it to expand them. So let's do that. Let's expand this guy using our properties. Expand it all the way. So first we can break it up into multiple products. So you actually end up getting this plus log 2 of x squared plus log 2 of square root y. You'll notice this is just equal to 3. You'll notice that we can move this to the front. And actually, because square root is technically an exponent, we can also move that to the front too. Alright, now let's condense 1. That's supposed to be log, sorry, and that's supposed to be a thing. Alright, let's condense. Let's just do it one step at a time. Let's do these two first. First, we can move these back. Right? And then it just becomes this. And now we're left with this. We do the same thing. Move this here, and then we divide. We're done. I mentioned earlier that logs are inverses of exponentials, and exponentials are inverses of logs. So we can actually use this to solve problems. So for example, we can solve for x. Let's move everything over. We can isolate e. And just so you know, ln is equal to log base e. So we're just going to ln both sides. That cancels the e on the left side. This gives us ln 19. And just solve for x. It's equal to ln 19 minus 1 over 3. You can plug that into your calculator and you should get some answer. Or you can leave it like that. Now, let's do some logarithmic equation. The thing you always have to be careful with logarithmic equations is you always have to check the domain. So, for this guy, the domain is -1, parentheses to infinity, and this guy is 0 to infinity. So that means the whole thing, the answers need to be positive, and they can't be 0. So to solve this, we're going to use properties of logarithms. We're going to combine these first two together, and we're going to get this. Log 6 of x squared plus x is equal to 1. I just multiply the x on the inside. Then we can erase both sides like this, get rid of the log, and that gives us x squared plus x is equal to 6. This is now quadratic. We're going to factor two numbers that multiply to -6. So in other words, x is equal to 2, and x is equal to -3. However, like I said earlier, we have to check the domain. Our numbers cannot be less than 0, and they can't be 0 as well. So -3 is off the table. Our only correct answer is x equals 2. And yeah, honestly, that's pretty much it for logs, exponentials, and it's not it for rational functions. Let me think of another example for rational functions. Let's graph something simple. Let's graph something like This is the case when the horizontal asymptote is 0. So, and you can tell my vertical asymptote is -3. This thing has no zeros, as you can tell, so we just have to plug in numbers. Plug in -2, you get 1. You plug in -4, you get -1. It's crazy. Okay. I think that's really it then for rational functions and exponentials and logs. Alright then, I'll see you guys in the next video.